Alright, so we went through this whole setup, and there's three key things. We have the area of OAT, the area of triangle OAP, and the area of sector OAP. And now we're going to make the following observation. Let's go back to our diagram. Notice that no matter what theta is, okay, now because we have triangles, it has to be between 0 and 89.999. I mean, of course you can't have 90 because you won't have a triangle anymore. But no matter where this theta is, notice that triangle OAT will always be the biggest triangle. And also notice that triangle OAP will always be the smallest triangle. And that no matter what angle I choose, this sector OAP will always be in between the areas of these two triangles. So let's write that out. We know that, here, let me write it down here. We know that the area of triangle OAP will always be less than or equal to the area of sector OAP, which will always be less than or equal to triangle OAT. That always is the case. Of course, these will all be equal when the angle is 0, because as this thing goes down to 0, then these all kind of converge onto themselves. But this will always be the smallest or equal, and this will also always be the greatest or equal to. So let's put in all of our pieces that we have. So let's see here, area of triangle OAP, that was right up here. Triangle OAP is the sine of theta over 2. So we have the sine of theta over 2 is always less than or equal to area of sector OAP is theta over 2. And that's always going to be less than or equal to triangle OAT, which is the tangent of theta over 2. Alright, so now we're going to work with this. And let's go ahead and multiply everything by 2. Let's get that out of there. So we have the sine of theta is less than or equal to theta, which is less than or equal to tangent of theta. It's actually kind of interesting if you think about that, and if you were to think about it, remember theta has to be in radians, but no matter what radian measure you get, the sine is always less than the radian measure, and the tangent is always greater than the radian measure. Just kind of an interesting little tidbit there. Of course, this is between 0 and 90, but it's still just an interesting concept that that's true. Alright, next we're going to multiply by the 1 over sine of theta. 1 over the sine of theta. So we're going to have the sine of theta. Here, I'll go ahead and do this in a couple steps. You have the sine of theta over the sine of theta is less than or equal to theta over the sine of theta, which is less than or equal to the tangent of theta over the sine of theta. Alright, so let's reduce this down. Sine of theta over sine of theta is 1. Is less than or equal to theta over the sine of theta. And this is kind of nice because this theta over sine of theta almost looks like the sine of x over x. It's just upside down. And we're using thetas instead of x's. Ooh, tangent of theta over sine of theta. That looks like some work. Let's see here. What do we have? I'm going to do a little side work over here. The tangent is the sine of theta over the cosine of theta all over the sine of theta. So remember, tangent, sine over cosine. So that's going to be the sine of theta over the cosine of theta times 1 over the sine of theta. The sines cancel. So this is going to be 1 over cosine. So less than or equal to 1 over the cosine of theta. Alright, and as I just said, this theta over sine of theta looks very close to the sine of theta over theta we want, it's just upside down. So now we have to take the reciprocal of every side. And so when you take the reciprocal of everything, well, 1 over 1 is just 1. This becomes the sine of theta over theta, and this becomes the cosine. And then we have that property that if you take the reciprocal with inequalities, you got to switch the direction of the inequalities. Good. All right, I need another piece of paper. You know this is fun when you use 2 pieces of paper. Okay, so all right, so we have this information, and I'm going to switch this around. So I'm going to move this to be the cosine of theta is less than or equal to the sine of theta over theta, which is less than or equal to 1. All right, so we went through this whole process, and we now have this, and this is set up for the squeeze theorem. So now use the squeeze theorem. All right. So we want the limit as theta approaches 0. So what is the limit as theta approaches 0 of the cosine of theta? Well, this one's not so bad because you just substitute in 0 for cosine and you get the cosine of 0, which is 1. What is the limit as theta approaches 0 of 1? Well, that's just 1. Well, therefore, if this is true and this is true, and the sine of theta over theta is always between these two, we can say that the limit as theta approaches 0 of the sine of theta over theta equals 1. And so there you go. There is our first special limit. The limit as x approaches 0 of the sine of x over x equals 1. It's pretty exciting. All right, so I mean it's a little complicated, this whole theorem and the proving of this special limit. But it's good to go through proofs. I mean, as you get higher and higher in math, you get more and more proofs, so you kind of have to be able to dissect how these proofs work and what they mean. So now we have this. But now that we've actually proven that that limit is true, we can use this, of course. We're not going to go through that every single time. So if we have, for example, let's say we want to find the limit as x approaches 0 of the sine of 4x all over x. And we want to find that limit. Now, of course, we would substitute first, but that doesn't work. We would get a 0 on the denominator. However, we have this limit. We now know that the limit as x approaches 0 of the sine of x over x is 1. We can use that for this. One thing about this, though, is the way this was proven, the angles, see, these are angles right here, and these values have to be exactly the same. So these aren't the same because this is actually 4 times whatever x is. But that's a fairly easy thing to fix, because what we're just going to do is we're going to multiply everything by 4 over 4. And we're allowed to do that. That's just 1. And then the key is, where do we place each 4? So this 4 up here we're actually going to bring out front, and this 4 here we're going to put with the x. So we're going to end up with 4 times the limit as x approaches 0 of the sine of 4x all over 4x. So this 4 we brought out front, this 4 we partnered with the x down here, and now we have the, this sine of something over that exact same thing, the sine of 4x over 4x. So this is 1 And so the answer is going to be 4 times 1, which is 4. Easy enough.